And today's topic is going to be motor operation and how PSC motors compare to EC motors in operation relative to total external static pressure and energy consumption, and what happens when we actually upgrade from one to the other. So our agenda this morning is going to be motor types and meaning. An analogy that I like to use, it's called the 3-cup analogy. Works really, really well with homeowners. An example home, and then comparing our analogy to testing the data. And what happens when we upgrade without understanding. So let's start with a motor that is in a lot of homes right now that we're slowly getting rid of and upgrading to the new EC motors, and that's the PSC motor. It's a permanent split capacitor motor. And what that is that's a type of single phase alternating current, or AC motor, or it's a type of split phase induction motor in which the capacitor is permanently connected. This motor is not controllable through a wide range, so it does not vary speeds. And that's that no intermediate speeds there. We do have speed taps that we get to select, though, and we have to understand how we're selecting and what we're selecting those to. And with the higher total external static pressure of a PSC motor, what will happen is the wattage consumption is actually lower. So that means that the energy consumption is going to be lower. And why is that? Well, that's because the higher the TSP on a PSC motor, what will happen is the CFM output becomes less. When the CFM output is less, the RPM is less, which means that the energy or the wattage consumption is less. How do PSC motors work? Well, we have a need for a mechanism to actually start that motor rotating. And what we do is we have two sets of windings. We have the main windings and the secondary windings. And what those main windings do is they're connected to the main power source. So that's what actually will start that first phase. And the secondary windings are connected to a capacitor. Upon turning on, the current will flow through the main winding first, and then with a short delay due to the capacitor and the secondary windings, that comes on. This phase difference, as we see here on the right bottom picture, well, the top ones are your two windings. You can see how those are opposite of each other, just like the secondary windings. And with that, the electric current, we can see how they offset. Now, this offset, or this phase difference is what we call it, causes the peak magnetic field to alternate, generating that torque for that motor to start and to rotate. So starting rotating and continuously rotating. So that's just a basic quick overview of a PSC motor. Now we have ECM, or electronically commuted motors. What those use electronic controls to vary speed, such as a control board, the powered pulses on and off with semiconductor devices or electronic switches or transistors. And these usually have power signals of 3 or more circuits within that motor. Now, by varying the timing and duration of those pulses, the electronic controller can accomplish speed control and maintain high torque at startup and over a wide range of speed. And with this, the TESP, or the total external static pressure, and the wattage consumption are going to vary depending on which type of ECM we have. Now, there are 3 main types of ECM. We have a constant CFM, we have a constant torque, and then a constant speed. So constant CFM is also known as constant airflow. Constant speed can also be known as constant RPM. The two most that we are going to see, and actually the most that we're going to see now as we start to replace these pieces of equipment, these motors, these furnaces, is we're going to see this constant CFM. Now, we may also see the constant torque. Let's look at those a little bit more, okay? So a constant CFM motor, a constant airflow motor, is one that we'll see like on our 59 TN6s, MN7s, the 58 CVAs, and those have that wide variety of speed range. So what this motor does is it reacts to the system's static pressure by adjusting that motor RPM up or down to maintain system design airflow performance. So those are those dip switches that we set up on a furnace board or within the Infinity controller or any other type of smart communicating controller that's out there. The constant torque motor is going to be a motor that reacts to the system static pressure by adjusting motor RPM up or down to maintain a pre-programmed torque setting for each speed tap. Now, where do you think that we will actually see this type of motor, guys and gals?
On air handler systems.
On air handlers, yeah, that's the very, very big one that we see them on. The FV, the Frank Victor model numbers of our carrier Bryants. That's where you'll see these here. And this is where you get to select your speed tap. These are also like an X13 style motor too, that you may see out there. And then we also have constant speed. Now, constant speed, we're not going to, or constant RPM, we typically will not find on indoor blower motor applications. So these motors do not react to system static pressure changes, and they continue to run at a pre-programmed RPM. And again, not commonly found on indoor blower motor applications. So the 3-cup analogy and how I like to understand what's going on within a home, within a duct system, especially when we have complaints and things like that, or we have high static pressure. So what I like to do is say, hey, imagine we have 3 32-ounce cups of water sitting in front of us. If I take this first cup right here over to a sink and I bring it back and I fill it with water, we should be able to take that cup that's full of water now and pour it into our second cup and fill that 32-ounce cup up with water. Once this middle cup is now full of water, I should be able to take that second cup here, the middle cup, pour it into the last cup or the third cup of water here and fill it up. Finally, once I have this last cup full of water, I should be able to then take this cup and fill the first cup back up and continue this process indefinitely. But what does that mean, right? How does that pertain to the airflow, the static, the ductwork that's in the home, and what's causing the differences of these motors and what's going on? Well, the home, the HVAC system, and the ductwork react in a similar pattern, except we can see water, right? We can't necessarily see air, but this gives a good visual representation of what's actually happening within a home and a great analogy to use with homeowners. So the most important cup is the middle cup. Without this middle cup, I cannot connect the other 2 cups. And that most important cup represents the home. The home determines the size of this cup right here. So again, if it were not there, you cannot connect the other two, and the home determines the size of the HVAC system or the size of the cup. Now, again, we want to make sure that the home and the load calculation and everything that we've done is the correct size for this cup, because that can affect obviously everything else too. So again, as we talked about last week, if we don't test, we guess on the size of the cup. The first cup here represents the return air, or the return air ductwork from the home. This is pulled back through the HVAC system by that blower, that motor, that PSC, or that ECM, through the return grills and the return ductwork, again, back to the blower of the HVAC system. Once that gets to the system, it's either heated or conditioned. And then the third cup represents our supply air or supply ductwork. So this blower then pushes it on a positive side. So it's sucking here, it's pushing it here through the furnace, the HVAC system, heating, cooling the system, and then back out to the home through the supply ductwork and registers. And then we keep continuing this process over and over. So examples of what we mean and how to represent that on that 3-cup analogy there. So here's an example of one that we ran, a 90,000 BTU gas furnace. We see here it's a 58 STA 090. So there's the 90,000 BTU. Anybody want to guess the beginning portion here of what this is? So this furnace here is a 80% single stage PSC motor, 90,000 BTU. The outdoor unit that's actually connected to this one is a 3-ton air conditioning unit. It's a PSC motor. And the reason for the call of what we were going out here and what we constantly see is tripping limit, not enough airflow through the extremities of the home, and the system shutting down. So no heat. So what I like to actually look at there is on top of this plenum, on the supply plenum, we had a certain amount of ducts coming off of this, and that's how we were actually feeding the air through the house. With that, we can actually get those sizes. So that goes over to here. So when the ductwork is visible and easily accessible, this is a great analogy to use and a process to go over with the homeowner. And what I like to do is I like to write it out. We have an AC size of 3 ton. Our nominal airflow that actually goes with that system is how it's from the manufacturer. Yes, we can adjust it, and there's a range that we can go to, but we're going to use 400 CFM per ton. When we multiply our tonnage by our CFM per ton, we can actually mark out our tons, and that tells us our CFM that we need or should have for that air conditioning unit, which is 1,200. From the product data of the furnace, the 90,000 furnace there with the PSC motor, it's calling for heat of about 1,375 CFM. Now, all this ductwork here is visible, so I can kind of see what's going on. So I, again, drew it up here and just kind of wrote up what we have. So we have a return 14-inch metal coming back to our drop. We have a 10-inch metal that goes up to the upstairs. It changes to flex in the attic. We've got 2 8-inch metal runs off the front, a 7-inch metal, and then a 4-inch metal round pipe. So what we do is we get all the sizes of the supply runs, the return runs back to the equipment here. Or you may have a trunk that comes off of it. You could have a trunk that actually comes to the return as well. So get those sizes, write them down. And what we're going to do is based off of that there, we have 1,200 CFM on the AC that's needed, 1,375 on the heat. So what we're going to do is we're going to assume, as we're in the home, that everybody's done their job correctly up until the point that you've gotten there, and that HVAC system is the correct size. So again, in this example, we're going to use that this is the correct size of equipment. So what we do is we write down underneath this cup here, because that's the home and the HVAC system, how much airflow is needed, 1200 to 1375. So our furnace 1375, our AC 1200. Ductwork should be sized for the highest CFM. So is our ductwork, or should we consider our ductwork size for the 1200 or the 1375 CFM?
1375.
Absolutely. So what we do is we fill our cup up. Let's break down our supply. Again, a little asterisk here. We're assuming the HVAC system is correct. And we're also going to use a rule of thumb. There's proper ways to design duct systems and things like that, I understand, but let's use a rule of thumb so we can at least get an idea and understanding of what's happening. So 10-inch metal, 8-inch metal, 7-inch metal, 4-inch metal, and write down the sizes here. How much air can each one handle? Well, you can see the metal here at our friction loss, which we're going to talk about in a second, is at 375 CFM. As soon as that changes to 10-inch flex, that duct can now only handle 250. Should I account for the 375 or should I account for the 250? 250. Absolutely. And that's because that's our smallest one. That's where our restriction is. If you have 8 lanes of traffic that go to 4 and there's a traffic jam at that point, well, everything else is going to be slowed up. So I look at it that way. I explain it that way with the homeowner, and they seem to understand that as well. 8-inch metal, 200 CFM each. Multiply that by 2 is our 400. 7-inch metal, 145. And then 35 roughly on our 4-inch metal, equaling 830 CFM. Friction loss, as I said, I'm going to use a rule of thumb on the supply. So if you have your super cool slide rule or you have your app or any other ductulator, what we're going to do is we're going to use our friction loss here of 0.08 on the supply. Give you a second if you want to write that down or remember that. 0.08 on our supply side duct system for our friction loss. This is an example here showing where I put an 8-inch round metal and then I changed my CFM volume to equal my friction loss. And we're at 200, which is exactly what I wrote down right here. Did that for each individual one to come up with our total number right here. So now that we know that we have 830 CFM, we can fill our cup here, our third cup on the side, which is our supply air side. And it's 830 CFM. Based on rule of thumb, okay, we're going to start at 0.08 on our friction loss for that supply side as shown on previous slide. Therefore, the supply ductwork can handle approximately 830 CFM of airflow. So we're going to break down the return side as well. We have a 14-inch metal. It's 700 CFM. And we're going to use a friction loss on the return side, rule of thumb, to start off with, of 0.05. So that's the second number you need to remember when we're looking at friction loss. On the return side is 0.05. Slide your CFM until you get to that 0.05, and you can see we're at 700. Again, based on that rule of thumb, we can start with that 0.05 friction loss for return. Therefore, the return ductwork can handle about 700 CFM of airflow. Now, when you look at this, we have a PSC motor. Okay? And we're wanting 1375 CFM from that PSC motor. what is going to happen to that CFM of that motor with the size of ductwork that we have in this scenario?
Stays in the furnace.
What happens to the airflow, the CFM? Does it go up, stay the same, go down?
Slows down.
Goes down.
Slows down. Now, how much does it slow down? Do you know? Does anybody?
130.
Slows
Depends
down
on-
by 130?
Yes.
Depends on the static.
Okay. So that's when we need more data. Okay. So now let's compare our cups to testing and the product data of the furnace. Okay. So I'm going to go over this. Hopefully we all know how to check static pressure now. I know we have some new people. So that's why I want to just spend a few seconds on this, or a few minutes on the slide here, to make sure that we're all on the same page of how we actually check a system's total external static pressure. Now, when we hear total external static pressure, a lot of people think it's in the return drop and it's in the supply plenum because, well, that's the total of everything, right? That is not correct. The total external static pressure is based off of that motor solely. And that motor is part of the furnace. So that's why it's part of our furnace product data. There are two numbers that we must get. There's four numbers that I recommend that an HVAC technician should actually check and test. And there's a reason behind it. So the first spot that I like to check is in the return duct as it's actually coming back down. You can check it up here. You can check it right before the filter. I usually like to get a direct line of path. So I'll go right before the filter here if I can. And then I'll get right past the filter into the blower compartment. You can go through where the wires input into the motor. If it's on a box, you can go into the box. If you take off this top door, and there's sometimes an access to actually stick your pitot tube and your static pressure tube down into your blower compartment, then you can get it that way. But start with the return drop. That's number one. And then we check into the blower compartment past the filter as point number two. Now, what we call that difference between those two is the filter pressure drop. Why is that important to get that number, guys?
It shows you basically what that filtration system is doing or how it's affecting the system, whether it's a 1-inch filter, a 4-inch filter, electronic air cleaner, air purifier, and so on.
Absolutely. Now, with a lot of these filters, because they're tired of us technicians and us HVAC guys and gals that are saying, oh, it's the filter. The filter's your problem. The filter can add to the problem. It's not always the problem. Okay. So what they've done to combat that is they started actually putting their pressure drop at a certain CFM on their filter. So it's printed on there. So you can pull out a Honeywell filter, you can pull out a Filtrete filter, and there's other manufacturers out there that started printing that data on that filter for us. And you can cross-reference your system CFM by checking your total external static pressure. Okay, or that filter pressure drop. So you can see what your filter pressure drop is based off of your CFM, which we get by checking our total external static pressure and comparing it to the blower performance chart and say it's running at that many CFM. Am I within range of that manufacturer based off of what they printed on that filter? So we can prove or disprove if that filter is the problem. So that's why I am very big on the 4 numbers, because it allows you, being in the home, to understand what's actually happening. And if we can suggest a different type of filter, or if we need to, for that matter. So the third point that I like to check is before the coil. You can go in the high limit. If there's a riser box in between the furnace and the coil, go there. If you can still get up closer to the top of this past the heat exchanger, that's where most people are going to tell you to check it. I will agree with that. However, the high limit is the most accessible with what we see and how systems are installed. And that difference between right below the coil or right at the coil before it goes through that coil and the high limit can be only, 0.01 inches of water column. That's not going to make or break us actually checking our pressures and how the system's operating. It's so minimal that it is okay to check in the high limit. And I wanted to make sure to clear that up. So that's our third point. And then we have our fourth point, which is then in our supply plenum. Point 3 and point 4, the difference of those two will actually tell us our coil pressure drop. Now, why is that important to know?
You could have a dirty coil.
Have a dirty coil? Yep. Now, how do you know if the coil's dirty? Based off of that pressure.
Coil product data.
Beautiful. If you look up the product data of that coil, it will tell you based off of how much CFM or how much air is running across that coil. And if that coil is either wet or dry, what that pressure drop should be. So there's our 4 points. Point 2, point 3. Okay, what you do is you take the positive side here and you subtract the negative side of the motor. So with that being said, you add these two numbers together. Don't worry about the positive. Don't worry about the negative. Add these two numbers together here. And that will get us our total external static pressure of that motor for that furnace. So again, if you only get two numbers, we want point number 2 right here in the blower compartment and point number 3 in the limit or right below the coil. Those two are the most important of how this motor is operating. But again, check the other two and understand the pressure drops across those pieces of equipment so you can better yourself and actually be able to diagnose a little bit better. So we're going to check the TESP, or the total external static pressure of this furnace in heating mode. All right. And my chart here only has 3 points. I didn't get the fourth one, okay, in the supply plenum. But again, if I'm only getting 2, this is why I'm using this example. I need after my filter, which is in my blower compartment, and I need before my coil. So we take our positive 0.38. We subtract our negative of our negative 0.6, add the two numbers together basically here, and you got 0.98. So then what we have to do, once we get our blowers, or once we get our static pressure here, as I like to know on this PSC motor, what blower speed tap is it at? How do we get that? Well, we verify it on the schematic for those blower speeds versus the color of the speed tap or the wire of the speed tap that's connected to the motor. So here's the actual picture of that circuit board with the speed taps of that PSC motor. We see cooling is set to black, which is factory. That tells me that's probably never been checked, adjusted, or changed. And then we have our heating speed tap down here, which is our blue wire. Great, we got blue and black. What's that mean? Look at our schematic, and then we can actually see how this is wired up. In cool, the black wire is high, and heat, the blue wire is medium low. Great, now we know. We have low, medium low, and high. It's got 3 speed taps on it. You can see here the red is low, the blue is medium low or medium high, and then black is our high. So I like to pull the product data as well to show the homeowner. Here's the 58 STA. That's our model number of our furnace that we're working on. It's the 90,000 BTU. It's the dash 14. I can go down here to the bottom and go, what's my certified pressure or static pressure for heating and cooling on this unit? Scroll across here, and heating is 0.15. Cooling is 0.50. Now, 0.15 in heating mode, especially if it's a lot more CFM than your cooling mode, it can be difficult to achieve. Okay, we obviously want to help lower it as much as we can, and I'll show you based off of that PSC motor and its airflow of what happens, of why we want that. But you can see here the airflow CFM in heating is 1375. In cooling, it can go up to 1385, which is that dash 14. So almost up to 1400 CFM. Now remember, our static pressure on our furnace here, our 090-14, was 0.98. So I like to highlight 1.0 because that's what we're closest to. We have our 3 speed taps. We're going to call it medium high on that blower speed for that black one. That's what it is. We take this number across here. And how much airflow is that unit producing at 0.98 inches of water column?
600.
600 CFM. What did it call for? What did it want?
1375.
1375. So you see how far that dropped down? It dropped down greater than over half of the airflow that that furnace wants. What do you think is causing that furnace to overheat?
Lack of airflow.
Lack of airflow. We're not moving enough air across that heat exchanger. The heat is sitting in that heat exchanger. What's a common thing that we do as technicians to that furnace?
Increase blower speed.
Increase blower speed. Turn the gas pressure down, right? There you go. There's the two I'm looking for. Turn the gas pressure down, increase blower speed. What's going to happen to that static pressure if I increase that blower speed?
It's going to get even higher.
It's going to get even higher. Do you think it's going to push any more than 600 CFM? Maybe a little, right? Maybe a little. Then you lower the gas pressure. And what happens when we lower the gas pressure?
Not getting enough BTUs.
We don't get enough heating capacity. We're trying to match the CFM versus actually correcting the issue. What else happens to that heat exchanger? Soot can happen. Yep. Has anybody ran a combustion analysis on a system that we've lowered the gas pressure outside of manufacturer specifications because of the scenario here? It's all over the place. I recommend if you have a combustion analyzer, which I do recommend that everybody has, and tests every unit that they go to, what I would suggest is look at it. See what happens to those numbers. I mean, you might be surprised. So now what we do is, man, we got a furnace that has some impingement, some damage of that the heat exchanger that's getting close. The homeowner's like, all right, let's just get rid of it. Let's get it replaced, right? I want to upgrade. I want a new furnace. And we go from a PSC motor to an ECM motor. And we send out our comfort consultants, our sales guys. And we go ahead and we put in Old Faithful. What I like to call Old Faithful is the 2-stage TN6 with a single stage AC. You guys see that quite a bit, don't you? So what we do is they come in, our comfort consultants do, and they do a like-for-like replacement with that system in the home. The only thing that we're upgrading is we're going from an 80, which you can see the flue pipe here on this one, upgrade from an 80 to a 90. We go from a 90,000 BTU to an 80,000 BTU because they can at least do that math. And this is what happens. So here's the product out of that. Here's the A17-14, okay, because they're going to keep it very, very similar on their portion with the like for like. So great job on their behalf. Then we come down and we look at the rated static pressure. We'll look at that. It's about the same, right? 0.15 in heating, 0.50 in cooling. Now we have two stages of heat. We have low heat, we have high heat. Low heat's at 1008 CFM, high heat's at 1240. Cooling can go up to 1310. It's fine. So there's our rated pressure. Here's our heating airflow, low and high, and then here's our cooling airflow up to 310 or 1310. What happens to the airflow of that motor? And what happened? We're assuming here TESP, the static pressure, is going to increase, right? But what happens to that airflow?
It's going to maintain CFM.
It's going to maintain.
Draw on the motor and eventually cause it to fail.
What kind of motor is that?
That'd be an ECM.
There's three types. Which one?
That's the variable speed, constant speed.
The constant airflow.
Yeah.
The constant CFM. Yep. Because you have speed, which is going to be RPM, and then you have your constant airflow or CFM. So that's going to be the constant airflow, constant CFM. So that TESP increases. Here's what happens with that, just like Josh said, it stays consistent or pretty darn close. So you see the chart doesn't go over 1.0. They definitely don't want you going off that chart. We were already at 0.98 with that PSC at about 600 CFM of air. And now we're going to put in a furnace that doesn't want to go below right here, 1008 CFM. And look at down here at the very bottom where it says low heat airflow. As that pressure goes up, the RPM is going to go up to try to maintain that airflow. Because if you remember earlier, we were talking about the constant airflow, constant CFM, ECM, okay, is going to raise or lower RPM to maintain that designed airflow. So it's obviously going to have to increase this RPM to try to maintain as close as it can. It still drops off a little bit, not too much. Where do you think this pressure is going to be on this unit that we just upgraded, even in low stage airflow?
It's all going to be on the motor.
But what's that?
Low
Is it going to be?
Low stage probably be about 1.1, high stage 1.3.
There you go. So that's exactly it. So we're off the chart, right? They don't give us this part of the chart or that blower performance, that fan curve. They don't give that to us for a reason. We don't want to be there. So if RPM goes up, okay, total external static pressure goes up, the airflow is going to stay pretty constant or close to. What's going to happen to the energy consumption?
It's going to go up.
It's going to go up.
So they're going to be spending more than they did with the PSC.
How many times have you heard that?
Lots.
Lots. Exactly. So we hear it constantly. So that's why we really, really want to talk about this, know this. This is why we ask for and recommend checking this on every single call. It's why we recommend and ask for it to better yourself, to protect the company, to protect service guys that have to go out and run warranty calls, on-call calls, after-hour calls. And we just keep replacing part after part after part. So if RPM goes up to maintain that system design airflow on that constant CFM motor, So the RPM goes up to achieve that, TSP increases, and if that static pressure increases and RPM increase, so does the wattage or energy consumption of that system. So the biggest thing that we want to do, especially prior to setting up either a like-for-like replacement quote with one of our comfort consultants, or if we set up a whole home comfort consult with blower door diagnostics and everything, I'll at least check that. I know Justin, I know Ronnie and other guys that actually go out and run those calls, they will be checking the pressure. But I'm going over this with everyone else to make sure that we check it. This is why we want to check it. This is why it's important. It's not only important to us as a company, it's important to the homeowner. They don't want to spend more money. They're paying more money up front on that initial investment to have a better piece of equipment that's supposed to be more efficient, that in turns being more costly and inefficient
Hey, Jeff,
after we install it. Yep.
What if we're on a job, either the blower motor is not working, so we can't, or we're on a job where the blower motor is plugged up and so's the evaporator coil. There's not a really good way to check the static on those jobs pre replacement.
Great question. So this is why I went over with you guys. The 3-cup analogy. Right? So if we can get the sizes of the duct that's immediately connecting to it, especially if the blower motor is out, we're setting up a comfort consultant to come out to do a like-for-like replacement quote. If we at least do something like this, that's very, very visible and easy for the homeowner to understand. And if it's easy for the homeowner to understand, should be easy for our comfort consultant to understand that, hey, our cup's short. We're not giving the unit enough air. We're not giving this other cup here in the middle enough water. We need to address it. Then that conversation is out of our hands. It's up to the comfort consultant to actually go over that with the homeowner, and it's the homeowner's decision at that point. And if we've done our portion, our comfort consultant's done their portion, and the homeowner declines, so it's an offer decline, to correct that, and they are educated upon their decision that they're making, we have responsibly avoided responsibility, and it's on the homeowner. Then when we go out to run those appointments or those calls, we can now say, we've had this conversation with you. You chose to not do anything then. Would you like to correct it now? And with that, we are at the end today, and I left plenty of time for questions and to go over even the last couple weeks if there's been any questions on our trainings thus far.
No, I just want